Good morning, students. Good morning, students. Myself Vijayawada-1, Department of Mathematics, K.B.N College. Today now we can discuss about Cali's theorem. Okay. First of all, we know that in this class we can discuss about state and prove Cali's theorem. First, we can define every finite group G is isomorphic to a permutation group. This is the statement. Firstly, we can write what is meant by permutation group. When we are saying that a group is permutation, if it is 1, 1 and 2, then only you can say that it is a permutation. First part we can prove it is a permutation. In the second part we can prove permutation group. Group means in the previous classes already we know that if it satisfies closure, associative, identity and closure. Closure, associative, identity and inverse. These four axioms are satisfied, then you can say that obviously it is a group. In the part 2 we can prove that it is a permutation group. In the final you can prove that this is isomorphic to a permutation group. Isomorphic means finally we can prove that it is 1, 1 and 2 and homomorphism. Okay guys, so first we can go by, first of all we can take the let G be a group. Okay, first we can take, in this group we can consider one element, let A belongs to G and X belongs to G. By closure law we can write that AX belongs to G. Okay, closure axiom A comma B belongs to G implies AB belongs to G. By the formula, if A belongs to G and X belongs to G, both are in belongs to G, then you can write that closure law AX belongs to G. Now we can define, we can prove that it is a permutation. First we can define a function, define a mapping, FA mapping from G to G such that FA of X is equal to AX. This is the definition. FA of X we can define as a AX. This is the equation considered. Now we can prove that FA is a permutation. Permutation means we can prove that well defined and 1, 1. In this first we can prove that it is a well defined and 1, 1. Well defined means you can consider x1 is equal to x2. You can prove f of x1 is equal to f of x2. Okay, that's why you can consider let x comma y belongs to G. We can consider two elements. Consider x is equal to y. Now we are multiplying both sides by a. Ax is equal to ay. In the definition we can write that ax, fa of x is equal to ax. So now we can write ax as fa of x, ay as fa of y. Okay, so finally you can prove that if x is equal to y, now you can prove that fa of x is equal to fa of y. This is well defined. Now we can prove that 1, 1. 1, 1 means we can prove that fa of x is equal to fa of y. You can prove that x is equal to y. So now you can go by reverse. Suppose consider fa of x is equal to fa of y. From the definition you can write ax is equal to ay. If G is a group, it satisfies cancellation laws. By using left cancellation law, we are getting x is equal to y. So up to down we can prove that well defined, down to up we can prove that f is 1, 1. Okay, so if fa is a permutation, firstly we can prove that fa is well defined and 1, 1. Now you can go for fa is onto. Onto means we know the definition. For each element in codomain there exists at least one preimage in domain. Then you can say that it is a onto. So let A belongs to G and X belongs to G. By closure law you can write it as AX belongs to G. Already we can define, let fa of X we can define it as a AX. So for all AX belongs to G, there exists X belongs to G such that fa of X is equal to AX. So మన కోడొమైన్ ఎలిమెంట్ తీసుకున్నామంటే దానికి ఇమేజ్ డొమైన్లో ఎగ్జిస్ట్ అవుతుందని తీసుకున్నాం. Then you can write it as fa of x is equal to AX. So obviously you can say that f is onto. In the case 1 we can prove that fa is well defined and 1, 1. Now you can prove that fa is onto. So finally fa is 1, 1 well defined and onto. So you can say that fa is a permutation. Okay, so in the theorem statement I can say that in this theorem we can prove three parts. First one is permutation, second one is permutation group, third one is isomorphism. In the part 1 we can prove that it is a permutation. Permutation means we can prove that well defined and 1, 1 and onto. So part 1 is over, fa is a permutation. Okay guys, now you can go by part 2. Part 2 we can prove that fa is a permutation group. Group means we can prove closure, associative, identity and inverse. These four axioms are satisfied, then you can say that it is a group. But now we can consider one more group. Consider G dash be the set of all permutations on G. So G dash elements and ఎలా కన్సిడర్ చేసుకుంటామండి? G dash is equal to FA such that A belongs to G, because permutation group elements అన్ని ఏ నోటేషన్ లో ఉంటాయండి మనకి? FA. So that's why you can write G dash be the set of all permutations on G. Now we can prove that G dash is a permutation group అని ప్రూవ్ చేస్తాం. So that's why G dash లో ఎలిమెంట్స్ అన్ని ఎలా తీసుకున్నామండి? FA such that A belongs to G. Okay, now we can prove that G dash is a group. Group means I can say that we can prove closure, associative, identity, inverse. Okay, first we can start with closure law. Okay, next closure law means let A comma B belongs to G implies మనకు తెలిసిన ప్రాపర్టీ అండి AB belongs to G. But in G dash all elements in the notation FA. So we can also consider FA into FB. Okay, so FA of, from the definition, FA of X means AX. So total you can treat it as this one is X, FA into BX. Again you can write FA of X. In the definition we can already define FA of X as AX. So FA, this total part you can treat it as X. So FA of X you can write it as A into X. Here X is BX. So A into BX we can write it as AB of X. AB of X in the above notation, AX we can write it as FA of X. So AB of X you can write it as FAB of X. Now I can write AB of X we can write it as FAB of X. So is it belongs to G dash, because all element G dash in the notation FA. So FAB of X is also belongs to G dash. We can consider FA comma FB belongs to G. Now we can prove that FA into FB is also belongs to G dash. So now we can prove that closure law holds in G dash. Okay, next you can go by associative. Associative law means we know the property A comma B comma C belongs to G implies FBC is equal to AB of C. This is the property. So in this property we can prove, we can take three elements FA, FB, FC. Okay, first FA into FB into FC. In the above property we can prove that FA into FB as F of AB. So directly I can write FB into FC as F of BC. Again you can write FA, you can treat this one is FB. Again we can apply closure law, FA into FB. Again F of AB. Here B is BC. F of A into BC. You can write it as these three are in multiples. So A into BC I can write it as AB of C. Okay, now I can write again closure law, F of AB we can write it as FA into FB. Again F of AB by using closure law, F of A into F of B. So left side we are considered as F of A into F of B, F of C, as we can write it as F of A into F of B, F of C. So clearly associative law holds good in G dash. Next so we are already proved that closure and associative. In the group we can prove remaining properties are identity and inverse. So in this first third one is identity law. Identity property we know that let A belongs to G, there exists E belongs to G such that A dot A is equal to E dot A is equal to A. Okay, so this way we can prove that this property. But in the permutation group all elements in the notation FA. So we are consider FA into FA. Again we can apply the closure law, F of AE. In this identity element we are multiplying any element, we are getting the same element, then you obviously you are getting F of A, FA. Similarly we can write that FA into FA. Again we can apply the closure law, F of E into A. If E stands for identity element, we are multiplying any element with identity element, you are getting the same F of A. So FE is identity in G dash. Okay, so identity law holds in G dash. So now we can prove that closure, associative, identity. And the last but not least we can prove that inverse law. Okay, let A belongs to G property means let A belongs to G, there exists A inverse belongs to G such that AA inverse is equal to E is equal to A inverse A. Now we can prove this property. A inverse is equal to E is equal to A inverse A. Right. Now we can consider FA into FA inverse. Again we can apply closure law. F of AA inverse. We know that closure property AA inverse is equal to E. FE. In the previous property we can treat it as FE is identity element. So you are getting FE. That means identity properties holds. Again similarly we can write that FA inverse into FA. Again we can apply closure law. FA inverse into A inverse into A. You can write it as FE. So FA into FA inverse is equal to identity element, and similarly we can prove that FA inverse into FA is also FE. So inverse properties holds. AA inverse is equal to E is equal to A inverse A. So obviously you can say that FA inverse is the inverse of F of A. So inverse law holds in G dash. So finally you can say that G dash forms of an permutation group. Is it clear? So in the part 1 we can prove that FA is a permutation. In the part 2 you can prove that FA is a permutation group. Okay, that permutation group we can name it as a G dash. So part 1, part 2 is over. Now we can prove that part 3. Now we can prove that G is isomorphic to G dash. Isomorphism means we can prove that well-defined 1, 1, and 2 and homomorphism. Okay, and that we can prove this condition. Then again we can define a mapping, phi mapping from G to G dash, such that in this proof we can define phi of A is equal to FA for all A belongs to G. Okay, right. Now we can prove that phi is well defined and 1, 1. Again in the part 1 we can prove that well defined condition is if X is equal to Y, then you can prove that F phi of A is equal to phi of B. 1, 1 means suppose if phi of A is equal to phi of B, you can prove that A is equal to B. So in that's why you can prove that these two conditions. First of all we can consider two elements, let A comma B belongs to G. First we can consider well defined A is equal to B, multiplying on both sides by X. Okay, again from the definition FA of X is equal to AX. So you can write it as FA, BX as FB. From the above definition, FA is phi of A, FB is phi of B. Phi of A is equal to phi of B. So if you can consider A is equal to B, then you can prove that phi of A is equal to phi of B. So phi is well defined. Is it clear? Now we can prove that 1, 1. Already we know that 1, 1 condition means suppose if phi of A is equal to phi of B, we can prove that A is equal to B. Now you can go down to up. Suppose if phi of A is equal to phi of B. From the definition, phi of A is FA. From the definition, FA is FB. In the equation 1, starting definition we can consider as FA of X is AX. FB of X is BX. Again G is a group, right cancellation laws holds. Suppose X is we are cancelling both sides, then you are getting A is equal to B. So phi of A is equal to phi of B. We can prove that A is equal to B. So up to down well defined, down to up 1, 1. That's why we can write implies and implied. Implies up if A is equal to B, then you can prove that phi of A is equal to phi of B. That is well defined. Suppose if phi of A is equal to phi of B, you can prove that A is equal to B. That is 1, 1. So isomorphism means we can prove that well defined 1, 1 on to homomorphism. So in these four properties we can prove that well defined and 1, 1. Now we can prove that onto. We can prove that phi is onto. Phi mapping from G to G dash. Onto means always we can took the elements in codomain. In the G dash all elements in the notation FA. So that's why let FA belongs to G dash and A belongs to G. Now consider phi of A is equal to, already in the definition we can write it as phi of A is equal to FA. Okay, so therefore for all FA belongs to G dash, there exists A belongs to G such that phi of A is equal to FA. So phi mapping from G to G dash, you can consider FA belongs to G dash. they are exist, A belongs to G, such that phi of A is equal to Fa. So you can say that phi is onto. Okay, in the above case we can prove that it is well defined and 1 1. Okay, next you can prove that phi is onto. Okay, now finally we can prove that phi is homomorphism. You know that what is meant by homomorphism condition goes to, if f of ab is equal to f of a into f of b, it's satisfied, then you can say that f is a homomorphism. But we can prove that it is phi is homomorphism, so that's why you can consider let a comma b belongs to G. Now consider phi of a into phi of b. Okay, as per the above definition, phi of a is fa, phi of b is fb. So now you can write phi of a is fa, phi of b is fb. So fa into fb as f of ab. Fab in the above definition you can write fa is phi of a, fab you can write it as phi of ab. So phi of ab. So homomorphism condition is goes to phi of ab is equal to phi of a into phi of b. Now you can say that phi is homomorphism. In the case 1 you can prove that it is a phi is well defined 1 1. In the next case we can prove that phi is onto. Next we can prove that phi is homomorphism. So phi is well defined 1 1, onto and homomorphism. In these three cases we can prove that, then obviously you can say that phi is isomorphism. Obviously you can say that G is isomorphic to G dash. Okay, this one is the Callis theorem proof. Is it clear? So in this theorem totally we can prove 3 parts. Part 1 is permutation, and the permutation we can prove that it is 1 1 well defined, 1 1 onto. Part 1 is we can prove that fa is a permutation. In the part 2 we can prove that it is a permutation group. Group means closure, associative, identity, inverse. These 4 axioms are satisfied, then you can say that it is a group. In the part 2 we can prove that it is a permutation group. In the part 3 we can prove that G is a isomorphic to G dash. That means G is isomorphic to a permutation group. Okay, in this case we can prove that it is a 1 1, onto and homomorphism. These 3 axioms are satisfied, you can say that it is a isomorphism. Finally you can prove that G is isomorphic to G dash. Okay, thank you.